Okay, so basically we kind of introduced the idea of lattices in cryptography last time, and then we started talking about some lattice properties, and I think we have to follow up from that a little bit. And the last thing we saw was the fundamental domain, the idea of fundamental domain. Right, and we just need a couple more things to properly measure. So we'll pick it up from where we left. The first notion is so we see that basically we have like bases, right? And the bases you can get from a base to another one, and then you have the fundamental domain, and you can shift it around and cover the space. Okay, so another important thing is if I have a lattice L and I have a fundamental domain F, then the n-dimensional volume of this fundamental domain. So if you see it in 2 dimensions, it's just this. Okay, but if you do it in n dimensions, it's like a volume, essentially. This is a name, and we just call it the determinant. And it's just like determinant of the lattice L. Okay? So basically, now you can think of all the vectors composing the basis of the lattice. What's the largest volume that you can obtain, right? If you take all the vectors to be orthogonal to each other, then you get the maximum, even in just 2 dimensions, right? That makes sense. Imagine that you have a rectangle, that's the largest volume you can get. If you just start skewing the 2 vectors, you get thinner and thinner. So it's the same thing in multiple dimensions. Ideally, you want your vectors orthogonal to each other, and that's the most, that's the largest volume you can get. So there is this important result, which is just called Hadamard inequality, which says that essentially the determinant of L is, by definition, the volume of the fundamental domain, and this is less or equal the norm of V1 times the norm of V2 times the norm of Vn. Okay, and it is exactly equal to that if the vectors are all orthogonal. Okay, so in fact, what we can do is if we have, if we write the vectors as rows of a matrix. So suppose that now we have, my base is V1, Vn, and I can express each Vi. See down there? Yes. I express each Vi as Ri1, Rin, right? And I just put them all in a matrix. So then I get that the fundamental domain is in fact given by the matrix R11, R12, R1n down to Rnn, Rn1. Okay, so it's like an n by n matrix, and then the volume of this is exactly the determinant of this matrix F. Okay, so that's very good, and the important thing is that the determinant is invariant for the lattice.
So no matter which basis.
Exactly. Independent of the particular fundamental domain that you choose, the determinant is always going to be the same. Yes, because every
fundamental domain or the basis.
So what you can, the proof is like this, because you can change basis from one basis to the other, right? If you're able to find the basis. So the lattice has a particular shape. Doesn't matter which basis you choose, right? That there is going to be a certain determinant there. So if you want to take the determinant to be like the one of your best bases, you can imagine, right? So you can then take another basis but the shape of the lattice doesn't change. Remember when we saw this? Now you can take a different basis for this, but fundamentally the shape of the lattice, like the distance between these lattice points, is that. Okay, so you're not going to be able to take, for example, here a basis that is like more orthogonal than this one, for example. Okay, so the determinant is a property of the lattice, because ultimately we're able to change bases and do this process. So the proof is not complicated. In fact, we can, if you want, we can actually go through it. If you're not convinced, what you can do is, if you have, suppose you have two different fundamental domains, V1, Vn, and W1, Wn. Yes? Then what you can do, you write down the associated matrices to these, like we did before. You just express them as row of the matrix. Okay? And then what is happening is that you're going to have that this is equal to that times a certain transformation matrix A that we saw last time. And remember that the determinant of A is plus or minus 1. We saw as the change of basis matrix. Right? So that is very simple to see that the volume of f of V1, Vn, which is equal to the absolute value of the determinant of f matrix. Right? Did I write absolute value before?
No.
I didn't. So maybe that's why you were confused. It's absolute value of that. Okay? And it makes sense because you're not interested in like positive or negative. You're interested in the magnitude of the determinant. Okay. And then, of course, this is equal to the determinant of is the absolute value of the determinant of A times f from W1, W1. And then, of course, this is equal to that A times that of f W1, W1. And of course, the absolute value, so the fact that it's plus minus 1 just means it's 1. So then that equal to that equal to that. So they have the same value. Okay, it's a simple calculation. Okay, so basically the determinant is like a good indicator, it's a good invariant. It's always good to have invariant for objects, right? Okay, so now here's where I was planning to start with lattices in cryptography. Of course, if you want to do cryptography, we need hard problems. And like for everything else, we've talked about hard problems. Now it's time to nail down like the hard problems that we use for lattices. Mainly, we use these. The first one is we call SVP, which stands for shortest vector problem. And it's simply asking, if you have a lattice L, find a vector V in the lattice, of course, non-zero, with minimal norm. Okay? And the second one, which we call CVP, or closest vector problem. Again, you take a lattice and you fix a vector in R to the M, okay, that is not in the lattice. Find a vector V in the lattice such that the norm W minus V is minimal.
These are the same. These are reducible to each other.
Exactly. That's exactly the point. Yeah. So basically, here you're asking to find what's the closest lattice vector to a fixed target vector, and this is like you're asking to find the shortest vector in the lattice. When you think about, I always think about it like in the coding theory point of view. Again, you can ask what's the lowest weight code word in the code, right, which is the minimal weight, or like given a certain word, what's the closest code word to it? It's really, yes, the distance. So, I mean, you're very right. The problems do reduce to each other. And you know, so we can consider normally CVP is like a little bit harder than SVP in a sense, because what you can do is that you can reduce CVP to SVP in a like little higher dimension. You need to take a lattice of dimension like n+1. But anyway, they are essentially the same problem. And sometimes we consider not necessarily the exact problem, but like some approximate solutions as well. And these are the basis of several cryptosystems. A couple of them we've already seen last time. Okay, so another thing that you may want to keep in mind is that, for example, instead of the SVP problem, we consider approximate SVP, which is basically asking to find a vector such that vector V is not minimal, but say is like less than epsilon times the shortest. So it may be enough for a crypto system if you have certain noise to be like within a certain radius of what's the shortest vector. You don't need exactly the shortest vector. So typically you have this epsilon to be like a function of n. Okay, depending on how big the lattice is, you may have an acceptable margin of error. Like so, that is good enough.
Epsilon, of course, greater than 1.
Oh yeah, of course, yes. But typically, yes, typically you're happy even if you just don't find necessarily the shortest vector, but like a short vector, which is like short enough. Okay. You also can think about, for example, the SVP problem with the shortest basis problem. Okay. Which is basically the problem of finding a basis V1, Vn that is like shortest in some sense. For example, you may want to ask that the largest vector in the basis is less than something. Right? So for example, you want like the maximum of the norm of Vi being less than something, or the sum of the norms. Typically, the sum, the square of the norms is less than something. Okay. So there's all sorts of like related problems here. Similarly, we have a version of approximate CVP as well. Okay, these are used in like more advanced crypto systems. Okay.
Yeah.
Okay, so this is the basic. I mean, it's just like we're not going to spend too much time on the actual problems, but let's try to move towards crypto systems. There's just a couple more things that we have to pin down. First of all, now that we're talking about shortest vectors and closest vector, like how big can we expect to be this shortest vector, right? This obviously depends on the dimension of the lattice, of course, it's like 2-dimensional, 3-dimensional stuff, and the determinant, and we're able to somewhat bound this. Okay, so first of all, there's a theorem by Hermite, which is saying that for every lattice L of dimension n, then there exists a vector V such that the norm of V is usually less than square root of n times the determinant of L to the 1 over n. Okay, we're not going to prove this because this is a little bit more complex than what we can do, but essentially there exists always a vector that is smaller than this threshold, and we also have a Hermite constant gamma n, which is the smallest value such that every lattice of dimension n contains a vector such that v squared is less than gamma n determinant of L to the 2 over n, which is kind of like the square of the previous one, essentially. And so in the version of Hermite's theorem that we presented, we have that gamma n is always less or equal than n, okay? But the exact value of gamma n is only known up to n equal 8. And you have, for example, that gamma 2 squared is 4/3. And so gamma 2 is the square root of 4/3, and so on. Gamma 3 cubed is 2, and so on. So you have certain known values of gamma n. In general, you have a certain bound, so you want to, of course, the lattices you're going to use in cryptography are not going to be dimension 2 or 3. So in general, you want to bound gamma n.
It's a little lower, you can see that.
Yeah. You want to bound gamma n, and there is estimates that tell you that this is between n over pi e and n over 2 pi e. Okay, when you know what pi and e are, of course. So, so this is already giving us an idea of where the shortest vector can be in terms of size, because I can estimate, I know by Hermite's theorem that there's always something below that threshold, and then the gamma n can be bound in this way. So you're trying to figure out that. And so, okay, so there is an important notion here. Basically, you can also formulate Hermite's theorem in a way that deals with more than one vector, because you can be looking at like shortest basis, for example, which is one of the problems we just introduced. So for example, you can say that the product of v1, v2, vn, so if you take the product of the norms of the basis, then this should be less or equal than n to the n over 2 times determinant of L. Okay, as you can see, all of these are always proportioned to the determinant, right? We said that the determinant is the invariant, so like how small is my vector or my basis compared to the determinant? And so basically, you know, one thing that we do know is the Hadamard inequality that I think we talked about last time. Yes, it was up here. See, remember that we said that the product, well, actually we talked about just earlier, the product of the norms is always at least as big as the volume, right? Or when we say like, yeah, the determinant is less than. You get the maximum one when they're all orthogonal. So you can look at it as like, okay, now the product of the norms is greater than the determinant of L. Right? If you look at it the other way around. So if you put that together here, you also have the product of the norms. And now you know that it's smaller than n to the n over 2 determinant of L. And so what you can do is you can define what we call the Hadamard ratio. And that should be intuitive, like the ratio of a certain basis B, V1, Vn, and that would be exactly H of B, well, a ratio, right? So determinant of L divided by V1, Vn. Yes, there you go. Okay, and then we'll take this to the power of 1 over n. Okay, if we do this, then we have the H of B is always between 1 and 0, and is exactly equal to 1, right? If the basis is exactly orthogonal. So it's a measure of the orthogonality of the basis, if you want. Right? On one hand, we know that the product of the norms is always greater or equal that, and then we get exactly 1, and then it's bound in the other way by the other. Okay, so I think we don't want, so in section 6.5 you have a lot of material on lattices that you're welcome to read yourself, but we cannot.
What section again?
It's 6.5.
6.5.
It is 6.5 that, well, we're looking at like the whole chapter 6 right now.
6 is all.
Yeah, all of chapter 6, but like 6.5, mostly we're not going to go in detail because there's like a lot more math that we can cover. But one thing that would be interesting now to look at is, okay, we define this like closest vector, shortest vector, and we have an idea of how big these vectors are now. How can I find them? Do I have a good way to do that? So it's kind of like a decoding algorithm, right? And this is what we're going to look at next. Okay, so let's start. So we're going to talk about this. Let's start with the lattice L containing an n with basis v1, vn. So the usual n-dimensional lattice now. And imagine that all the vectors are pairwise orthogonal. And so that basically means that vi dot vj is always 0 for all I different from j. And what we claim is that then in this case, if they are exactly orthogonal, it's going to be easy to solve the problems. And then what you can imagine is that the closer they are to orthogonal, the easier it will be. So we're making ways in that way. So
For orthogonal, don't we already have the solution?
well, I mean, no. So we have an algorithm which we're going to present next that tells me exactly how to do that, to find what the shortest vector is or the closest vector is, which is kind of the same thing. Okay, but the problem is that, like, okay, it's going to be very hard to have like a lattice that has exactly a fully orthogonal basis, right? So if we have something with like, we introduced that measure of orthogonality just now with the Hermite ratio, the Hadamard ratio, and the closer we're going to be to orthogonal, the easier it's going to be to solve the problem. Obviously, for cryptography, we want this to be hard, so you can see where the trapdoor is going to be, but one thing at a time. Okay. So essentially, supposing we're trying to find the shortest vector problem, which is the easier formulation, right? So the length of any vector, right? If we take a vector in the lattice, this is going to be a certain a1 v1 plus a2 v2 plus an vn, right? Because that's the basis. So if I take the length of that, norm squared. I hope you're okay with the norms. I remember the norm is defined as the square root. Okay. So then this is going to be exactly a1 squared norm of v1 plus an squared norm of vn. I also have to square these. Okay. Now remember that the AIs are integers because this is a lattice. And so then the shortest vectors in L, in this case, are simply plus minus v1 plus minus vn. Okay, which is good. So now this is, so when we try to solve SVP, we just look at the shortest vector in the basis, essentially. Okay, and now if we are trying to find the closest vector, so suppose that now I have a vector w, which is t1 v1 plus tn vn, and this is not in the lattice, right? So now these values ti are reals because I'm not in the lattice. Okay, well then what do I do? Basically, I have that the norm of v minus w squared is in fact a1 minus t1 squared norm of v1 squared, and then an minus tn squared norm of vn squared. And again, the AI are required to be integers, and so this norm, which is the distance, right? We want this to be the closest vector. This is minimized if we take the AI to be closest to that. So basically, we're just going to take like the round down or round up of the I, right? This is, so floor and ceiling. Floor is the closest below and ceiling is closest above. We're just going to take either or, whether it's because we want really the nearest integer. And that's it. That's the idea, essentially. Okay. So now this is working if my basis is fully orthogonal. But let's see how we can do it with bases that are not fully orthogonal. Okay. So now let's try to use fundamental domains. Right now, suppose that I have a basis V1, Vn, and I'm trying to use fundamental domains. We know that if we take translates of F, we fill the entire space. And so basically, every vector W of this form is a translate. So this is basically F plus V, right, for a certain V. So what we would be tempted to do is that we take the vertex of the fundamental parallelepiped that is closest to W at our hypothetical solution, right? So what we can do is that we can just write W as V plus epsilon 1 V1 plus epsilon n Vn, and all these epsilon i's are between 1 and 0, right? Actually strictly less here. And so we take epsilon I to be 0 if it's, for example, less than a half, and we put 1 if it's greater or equal than a half. So we're trying to approximate. Okay. The idea is exactly this one. So I'm not going to draw it again because you have it on the book. But you see, if you have a vector W, what you're going to do is you're going to look for the closest point in the fundamental domain, right? And this is a candidate for what the approximate closest vector is. Okay. Remember that the fact that these are between 0 and 1 because we are within the fundamental parallelepiped, right? Okay. So in this is just 2 in the 2-dimensional example, just to decide the x and the y essentially, right? But in n dimensions, you see, like, for every component, you're going to see whether it's like more than 1/2 away or less than 1/2 away, and then like you're going to go towards the closest point. So it looks like this should work, but then, you know, this thing can happen, and you know, maybe we can see it in the picture, maybe not. Maybe if we zoom in a little bit. So if you take the same lattice, that's the same lattice, okay, same 2-dimensional lattice, and you have this basis here, you see it's exactly orthogonal, right? But I could also choose like this completely weird basis. As long as there are 2 linearly independent vectors, it works. And so now what can happen is that this basis is good and this basis is bad. And how you determine that is the angle between the 2 vectors. Right? If the angle between 2 vectors is maximal, remember that at most you're going to have 90 degrees because they're orthogonal, then it's a good basis. If the angle is very acute, then it's a bad basis. And when you have a bad basis, this procedure is not going to work very well. Because when you try to approximate, you're going to go towards a basis vector that is like super skewed, but that's not necessarily the closest one. Okay, so if we try to solve CVP with a good basis, we're likely to succeed with this simple approximation procedure. But if we use a bad basis, then that will point us to the wrong vector. Because when you measure the basis, like, it's so skewed that you think, oh, that's the closest one, but actually you have a lattice point much closer than that. So then this is really how the algorithm works, which is due to Babai. Algorithm for closest vertex. You write W in this way, right? And then you just set exactly AI equal to the rounding of each TI. And then you return V to be exactly, where do I have it? AI, VI, which is exactly the closest vertex. Okay? So the solution is V equal A1, V1 plus AI, Vn. Okay? So we did all the job already. But in the book you have a pseudocode which is really 3 lines, right? So it's just like basically you're just taking the closest vertex there. I think in this case, a couple of examples will do wonders to show why it works with a good basis and why it doesn't work with a bad basis. Okay, so let's go through that. Let's take a simple 2-dimensional lattice. And this is great. I think that is great that in lattices you can do 2-dimensional examples, for example, and they show you exactly how the things work. This is easier to visualize than with linear codes.
Even though it's not cryptographically secure.
Of course not. But for example, in terms of basis reduction, this really illustrates what the problem is in this case. So for example, I take these two vectors, 137, 312, and 215 minus 187. Okay, in 2 dimensions it's super easy, they're not independent, just not a multiple of each other. So now let's find a vector in the lattice defined by these two vectors, right? And suppose that the given vector is W, which is 5, 3, 1, 7, 2, and 8, 1, 7, 4, 3. Okay. All right. Yeah. Okay. Yeah. So that's a combination. It's gonna be a combination of these two. So what we're gonna do is just write W as T1V1 plus T2V2, and you can do it with linear algebra, right? You want, for example, 53172 to be T1 times this plus T2 times that, right? So you're actually writing W as T1, T2 times the two vectors. It gives you a system of equations, right? You know how to do that. And it's easy to solve for that. For example, you can invert the matrix, right? And then you find T1 equal approximately, I lost it, 296.85. And then T2 approximately 58.15. Okay? So this is simple linear algebra. Of course, again, it's dimension 2 and it's not cryptographically relevant, but it's showing us that with this basis, what we're going to do is that now we're going to round these. This we round up to 297. So we're going to take V to be 297, V1, plus this we round down to 58, V2. And we do that, and we get the vector 53159 and 81818, which is not even close to this one, right? And in fact, we find that the distance between V and W is approximately 76.12. Okay, what that means. And so this is actually quite small. Why this works is that, in fact, these two vectors are quite orthogonal to each other. They are not exactly orthogonal. You can compute the dot product. It's not 0, but you can compute the Hadamard ratio, right? And you find the H of V1, V2 is, remember this is in this case determinant of L divided by the product of the two norms. And then you take 1 over dimension, which is the square root in this case. So when you do the calculations, this is about 0.977. Right? This is actually nearly 1. So it's a very good basis. Okay, now let's try to solve the same problem. What's the vector closest to this? In the same lattice, if I use a different basis, right? Let's use, I can't use W1, so this is V1 prime, which is 1975, and then 438. And V2 prime, which is 7548, and then 1627. Okay. Now, one thing you can notice already, this one had a negative component, right? So you can imagine like it was actually, okay. In this, all components are positive, so it's more the case of like, yeah. Actually, if you're curious, this one is 5V1 plus 6V2. And this one is 19V1 plus 23V2. So you see it's a linear combination of the previous basis. Okay, great. If you do the matrix as determinant 1 minus 1, everything, all that. Now we do the same procedure. Basically, we do T1, T2, but with this matrix. So 1975, 438, and then 7548. And 1627, same problem, right? It's the same thing. We apply the same technique. We find the solution T1 approximately 5722.6, and then T2 approximately negative 1490.34. Okay, so we're gonna have to look this up. So then we set our solution B prime to be 5723 times V1 prime minus 1490 V2 prime. Yes, it's the exact same algorithm, right? And then what we find when we do the calculations is the vector 56405 and then 82444. Now this is a lattice vector, right? But it's not that one. You can see that this one is farther away from the original one. You can compute the distance. The distance between V prime and W is bigger, is approximately 3000. Yeah, well, the previous one was 76. So, you know, regardless of like in absolute how many, you know, what these values mean, but you can see even in proportion, this one is much farther away from the. So we found another lattice point. It's not that we didn't find a lattice point, but it's not the closest one. And I didn't know if the previous one was the closest, but it is reasonably close, and this is certainly not close. Okay, and the problem with this is that when we compute the orthogonality of the new basis, we actually we do the same process that we did here, and then we get the h of V1 prime, V2 prime is approximately same thing, but we find that this is 0.07.
Really far.
So it's a really bad basis, okay? And so what happens, I think the book illustrates it better than I could possibly ever draw it, is that you see when we have this basis that is very skewed, and we take our target point, this is the closest lattice point, but the closest vertex is this one. Right, so I have a bad parallelepiped to begin with, and so the closest vertex is not going to be anymore the closest lattice point. Okay, and that's exactly what happened in this example. And I think in this case, as an exception, seeing some numerical values really does help understand, like, okay, the distance gets bigger, and the orthogonality value is not good in this case. Okie dokie. Everything makes sense so far? We're building, right? So we have now definition of lattices, and we have problems. And we've seen that essentially, even at a very intuitive level, we have one algorithm that works very well for good basis, and won't work for bad basis. And that's enough to build a factor, right? So what I want to do then is have a good basis and hide it into a bad basis. And then the person that has the good basis can decode, if we were doing linear coding theory, and the person with a bad basis cannot do anything. Or can try, but that's a different matter. Okay, so several crypto systems were then created, usually in the mid-90s, so a little bit later than McLeish started in 78, and then Internet started looking at this in 1985, and then like people were looking at coding theory-based crypto systems. Crypto systems based on lattices came a little bit later, and but they have been very popular since, and even more popular in recent times when we started to worry about post-quantum problems. Okay, so they definitely came out in the system before people were worrying about quantum computers, but they were already an interesting alternative with certain advantages and disadvantages compared to Al-Gamal, RSA, and the elliptic curve stuff already. Okay. So the idea, what we're going to show is the GGH crypto system, and the idea is exactly the one that we have discussed, where essentially my private key is a good basis, and my public key is a bad basis, and my message is going to be a binary vector that I use to form a combination, right? And then to recover my message, I have to use the algorithm to find the closest vector. So we can discuss, I think, later the features of these systems. And first I want to show what the crypto system looks like, if that makes sense. Okay, so let's start. So the key generation, we start by choose a good basis. And I assume by this point it's clear what I mean by good and bad basis, right? V1, Vn. Okay? And so I want this to be like reasonably orthogonal to each other. And one way to do this, for example, is you can fix a parameter d, and then you choose the coordinates of these vectors between like d and minus d, so in a small interval, okay? At random. And then you can check in the end, once you compute your basis, you can check your Hadamard ratio and then see how good that is. So that's kind of comparable to what people do, say, generate primes or something like. You just do it at random and then you check, you know, like if it's a good candidate or not. So here it's even more relevant because you're doing it in a probabilistic way. Like you don't have an obvious way to choose like a reasonably orthogonal basis, and you want it to be random, right? Always.
There are obvious ways to choose an orthogonal basis.
An orthogonal basis, yes.
We don't want one.
But we don't want like a fully orthogonal basis.
So that's
And the thing is, you want your basis to be as random looking as possible, because we already saw that if the private key is too recognizable, then it's easy for an attacker to launch an attack. So you can imagine that this is exactly the same thing as a person choosing a parity check matrix for a code that he wants to decode, but that parity check matrix cannot be, I don't know, a Hamming code where all the columns are exactly the binary. That's too much. So you want something that's like still kind of like a random looking, but still allows you to do your magic. Okay, so you know, again, what you do is you kind of randomly choose these vectors, and then you check that the orthogonality ratio is, the Hadamard ratio is good enough. So there's like a lot of little parameters that you try to satisfy. Okay, and so then you store this as your private key, and then what you do, you just want to transform this into a bad key, public key, which is a bad basis. So if you imagine that V, big V, is the matrix associated to this, right? When you put these vectors as rows, so it's like V1, Vn, then you choose a matrix U, which is a change of basis, right? Such that, so the determinant is plus or minus 1. You can do this at random. And for example, again, one way to do this is you create U as a product of many randomly chosen elementary matrices. This is likely to enlarge the entire process. So you can choose like an elementary matrix, another one. They all have determinant 1 or minus 1. The product's going to have determinant 1 or minus 1, but you're like mixing a lot. And so then you can compute the new basis as like UB. And hopefully this matrix W, W1, Wn is the new basis, and it's not as good. Okay, again, you can check the Hadamard ratio. So now, if you want to encrypt, you have this public key. Right, so this Alice was doing this key generation, and Bob wants to send a message to Alice. He will take the public key, and what he will do is that he select a vector M as his plaintext. For example, M could be binary, but it doesn't have to be, but this is like the simplest choice, okay? And then you also have to choose, so this is going to be your message, and as we've seen before, both in Michaelis and before that in other probabilistic crypto systems, including the elementary one that we saw last time, you have to choose some noise. And so you're going to choose a vector R, which is like a perturbation vector or noise vector. And again, you're going to choose, here was D, here we just say like between delta and minus delta at random, right? Again, this is a fixed public parameter, is the amount of noise that the system can tolerate. So now you're trying to get into a vector that is not in the lattice, but like also not too far away, yes? Because obviously things start to degrade. So you can imagine that this is the equivalent of choosing an error vector with a certain Hamming weight in the coding theory case. Here, instead, we are perturbating by moving each coordinate by a little bit. Yeah, so again, in the two dimension, it's like the x and the y. You move the x a little bit and the y a little bit, you're reasonably close to the vertex. But if you choose this too big, then you're going to end up next to another vertex, right? And then your algorithm is going to fail. And again, this is in coding theory. We have the code words with our ball around, and it's the idea that if you change too many positions, then you're going to end up in one of the other balls, and you don't want to do that. So same thing here. You just change it, but the metric is different. You're not flipping bits. You are perturbating every position by a small integer. And then, I mean, basically what you do is the same thing, though, because your ciphertext is going to be MW plus R. This really looks like Elise, essentially. Yes. So by MW, it means obviously MIWI. Yes. So it's a combination of the bases. It's going to give you exactly a lattice vector, and then you add the noise. Okay. So of course, this is not a lattice point, but hopefully, when we use our algorithm, we can find the closest lattice point. Right? So what we do is that after, in the decryption phase, you simply apply Babai's algorithm, for example, and find the vector v. So apply the decoding. For example, Babai's algorithm. There's more sophisticated ones, of course, as you can imagine. And find the vector v that is closest to C. And then you just do v times w inverse and recover m. Yes, because remember that your message was actually not the vector, but was like the combination that gave you that vector. Okay, again, this is pretty much like applying a decoding algorithm to my code word, to my noisy code word. Okay, so that is the idea, and it may be worth making an example. So the point is that now, of course, if you have only the public information, then you only have the basis W, and your algorithm is not going to work very well in practice, right? And we'll talk about that in a second.
And you create W such that the
So you want your Hadamard ratio to be big.
Hadamard ratio is small.
Yeah, very small. So then your algorithm is not going to work, and then basically you're trying to find the closest vector as like a brute force. I mean, of course, it's not going to be pure brute force. You can do like some refinements, some birthday paradox stuff, but you don't have a lot of tools, right? So again, this is the same idea as that, like, if you see a random code, you don't have much in the ways of tools to decode. But if you have
collision attack,
yes, you can do better things, but not the main one. So here is a very simple instance of GH with a three-dimensional example, and we have V1 equal minus 97, 1919, V2 to be minus 36, 30, and 86, and V3, which is minus 184, minus 64, 78. So these three vectors are a good basis. You can check that the Hadamard ratio in this case of this basis here is approximately 0.74. Okay, so it's orthogonal enough. You compute the determinant divided by the product of the three norms, and then you take the cubic root. Right? Now you choose a random change of basis matrix U, for example, 4327, 3297, and 5464, minus 15447, minus 11770, minus 19506, and the last column is 23454, 178, 71, 29617. Yeah, and well, the determinant of this is -1, so it's a good basis. You multiply it with W1, W2, W3, and you get a really bad basis. This one. I'm not going to write it down, but you see it's like huge compared to the original one. And when you compute the orthogonality ratio of this, the Hadamard ratio is actually of this new basis W. You know what I wrote B here is B. Excuse me. Turns out to be about 0. Okay, so it's a really bad basis, which you could have the intuition of. All right. So now you choose a small vector to be your message. In this case, Bob chooses, for example, 86 minus 35 and minus 32. Again, the easiest thing is just choose a binary one. Yeah, but you can probably play with it a little bit more. The error, though, we want it always to be very small. So typically, this is like -4, -3, 2, something like that. That's the proportion. Yes. And then you just do this times that plus error, and you get your ciphertext. And now, Alice will use Babai's algorithm. So the ciphertext that you get is W. Actually, that's U. W I didn't write down, but it's like U times the basis V.
M is not binary in this case.
No, it's not binary. No, it doesn't have to be.
Okay.
It's as long as it's small, but it's a different type of small, though. Okay. Plus R, and you get the vector. Oh gosh. -790. 81427, blah blah blah. Huge coordinates, right? So very far from the actual base, but you can find. So now you're gonna find the closest vector to this base using this basis and the decoding algorithm. Yes, and then so you can write this as linear combinations. This is going to be 81878.97 times V1 minus 292300 times V2 plus 443815.04 times V3, right? And we find the vector in that basis is always an easy thing. Now we have to round. In this case, we don't need to round. We round up here and down here. This becomes 81879. This becomes 443815. Of course, the basis is very small vectors, right? My target vector is quite huge, so. So there's this kind of magic. So the message can be non-binary or can be something, so it makes the actual vector large, and then the noise wants to be small compared to the size of the vector. Yeah. So if this is too close to the actual basis, if you're too close, then it's again easy. So, well, then you find this, and then you recover exactly the vector that is closest to C. Which is going to be, for example, in this case, when you round this and you round this, you find the vector minus 79801423. You see, this is nearly that, and same for the other two coordinates. And you can see that this is close to that one. You can then compute the distance and see that that is really quite close. And so this is a lattice vector now, because you round it up and round it down, right? And so you write 81879 V1. This is the same, 443815 V3. That gives you that. This is this, and you found the closest vector. Once you have this, you multiply by W inverse, and you're done. Okay? Now, if you try to do this with the public basis, what you find instead is that C is 75.76 W1 minus 34.52 W2 minus 24.18 W3 You see now my coefficients are going to be smaller, right? Because my basis has bigger vectors. And when you do the rounding part, then this is 76 W1 minus 35 W2, and then minus 24 W3, right? This is going to be the lattice vector that you find using the same decoding algorithm, but using the bad basis, and then it's going to give you a vector that is not useful. You get minus 79, 50, 8353, and the other coordinates. And you can see that, look, this is already up here, so by several orders of magnitude bigger than the actual closest vector that we were looking for. And I clearly, in fact, in the first case, what you can compute is the distance between C and the first vector that we found. This is C. This is the vector that we found with the good decoding, is like 5.38, and the distance of this one, let's call it V prime, that we found using the algorithm with the bad basis, is 47200. So very, very far away. Definitely not the lattice point that we were looking for. Okay. So of course now GGH is not secure in dimension 3 or any small dimensions, but that's the idea of the crypto system.
Now, why can't we do something simple and pretty stupid like W inverse times the whole thing? And then round.
Because, so if you have that, then you get R times W inverse, and then that's huge.
Oh, W is huge. Okay.
Right? So, yeah, so in principle that's the thing, like you have the error factor that you can remove, but only if you have the good basis. Okay. So now I want to say a couple of things about GGH, a couple more things to conclude. So typically, does it make sense? GGH, I mean, you can see this, and it's really kind of like the equivalent of what we do in coding theory with Meckel. It's very similar. But the underlying mechanic is a little bit different because the metric is different using the little coordinates rather than the. Okay, so roughly speaking, basically, what you have for, say, Al-Gamal, RSA, etc., is if you want lambda bits of security, you essentially have an order of lambda cubed operations for encryption and decryption. In the particular case of RSA, for example, encryption and decryption are exactly the same thing. You do an exponentiation, and then you get this kind of like roughly, very roughly, like a lambda cubed. Whereas for encryption and decryption, for say lattice-based and code-based crypto systems, you get something like O lambda squared. So you get a speed advantage, and it's very easy to implement too.
The big speed advantage, but also a key sizing.
But the key size, of course, so yes. So the problem with this is that definitely in both Meckel's and this kind of example, then the key is something like n squared compared to RSA, for example, where you have. In fact, you need for GGH, you need a bad basis for the lattice, which is n squared numbers, and each number is like n log n, so then you get like n cubed log n. This is pretty big, and then there are some tricks to reduce this down to like n squared log n, but it's still much bigger than RSA. Okay, so you need to make sure that the CVP is hard. You can see that the one-way CPA security is based exactly on CVP. Easy. So actually, you can write it here. Obviously, the one-way CPA is exactly CVP. Okay. So you want this to be hard, and for this you need like n, say like bigger than 300. Okay. But in this case, then we have to see. Then we have to talk about. Attacks now. Okay, so GGH is a point of start, but it's too purely related to CVP to actually be practical because it leads to a key of something like 128 kilobytes. And again, this is similar to like the naked Michaelis crypto system that we saw at the beginning, right? Where already like in 78, it was like 67 kilobytes for like small-ish parameter would be considered now because it's like 2 to the 60. So now for bigger parameters, we get even bigger than that. So, okay, so what is the threat? So yeah, so both these kind of approaches with lattices and codes lead to like speed, because it's, for example, the encryption is just like matrix vector multiplication with like some perturbation in both cases, right? And for example, in the case of Michaelis, it's even binary arithmetic, so it's like super basic.
It's not even L squared because you can do it in parallel.
Yes.
Whereas you can't do
So
it.
it's very, exactly. So it has, beyond the speed advantage, also like implementation advantages, like people that like to code, you understand this, right? So, but the problem is the size, and then of course the security needs to be studied properly. So in the case of Michaelis, one of the problems was the structural attacks, exposing your key if it was too structured. And then other than that, if you assume that your key is not recognizable, then you have like kind of like the generic decoding attacks like information set decoding, and then they can be sped up with the collisions and things. And similarly happens here. So here, what is the point? Now, I'm trying to, if I have a good basis, I know how to solve it. So I have only a bad basis. So it's what we call lattice reduction algorithms, because you're trying to find a good basis from a bad one, okay? And what we will see is that there is an algorithm called LLL, which stands for Lenstra, it's two different Lenstras, Lovash, and it's exactly able to do that, to reduce the lattice base to a good one. Okay, so maybe we can see quickly an example in dimension 2, and then just mention that this is just like a generalization because the actual LLL algorithm is not obvious at all. Okay, but a simple example would be this. Now, and again, if you have a little bit familiarity with geometry, this was already done by Gauss, and I think I mentioned that already. Suppose I have a two-dimensional lattice, right? And I have V1 and V2 as a basis, right? Essentially, without loss of generality, let's take V1 to be the smallest of the two. Yes. How can we make V2 smaller? We can subtract multiples of V1. Yes, so what we can do is that we can just create a V2 star, which is essentially V2 minus certain multiples of V1, which you may have seen this, is V1 times V2 divided by normal V1 squared. Yeah. Why do we do this? Because then this vector here is the projection vector, right, of V2 onto the orthogonal complement of V1. Right, it's exactly this. We have V1, we have V2, but I have to be precise. This is V2, and V1 is smaller than V2. This is shorter, this is V2 is longer, and this is the diagonal of a rectangle, so this is bigger than that. So what we're going to do is we're going to project not onto V1, but onto the orthogonal complement, so this one. Right? And this we're going to get V2 star here. Okay. Of course, in this case we're kind of cheating because V2 star is probably not likely to be in the lattice, right? To be in the lattice would have to be an integer coordinate, but yeah, so we're only allowed to subtract like integer multiples of that. So the best we can do is basically something like V2 minus mv1, when m is in fact the rounding of that thing, v1, v2 dot v1 squared, okay? And this is, basically, if this works, good. If v2 is still longer than v1, then we're done. But if it's shorter, then we have obtained a shorter basis. And then what are we going to do? We're going to try again. Yeah. So you swap the roles, and then you try to project V1 onto V2. And this way you're like, tuck, 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 and you one step at a time, essentially, like, create a shorter basis up until the point
when those numbers is 1, then we're done.
Then you're done. Yeah, as soon as, like, if you do this, and your new V2, your V2 star, is still longer than the other one, then there's no way to reduce anymore, essentially. And again, this is because we cannot take the actual projection, we take like a rounding, so it may be that the next integer multiple is still longer than the one. So essentially, the Gaussian lattice reduction is like a loop, right? And like if V2 is smaller than V1, you just swap them, and then you just compute M, which is this. I'm not going to write it again. And then if M equals 0, you're done. Return V1, V2 as a basis. But otherwise, replace V2 with, like this, V2 minus M. Okay? So this is like nicely written as an algorithm, or more or less, with my calligraphy, but like essentially you're using the same V1 and V2 and just overwriting them, right? You replace V2 with a new V2, and then you swap. And then you replace V1 with a new V1, then you swap, right? And then you do this until you can. At some point you will find that M is equal to 0 and you're done. That's your basis. Okay? So when the algorithm terminates, then the vector V1 is the shortest one because you keep swapping, right? And so this algorithm is actually solving as VP2. And you know that in 2 dimensions you have the angle, you do these things. For example, in trigonometry, so the cosine of theta, which is the angle between the 2 vectors, is actually less or equal than V1 over 2 V2. And so in particular, we have that theta is always between 2 pi over 3 and pi over 3. We need a little bit refresh of trigonometry, okay? But like essentially, this is what we do. And I don't know if we need to see like a numerical example of this or not, but why not? We're okay. Very quickly. So we take V1 to be 66586 820 and 65B54729, and then V2 to be 6513996, and then 6393464. Okay, so that's my basis. I'm going to try to reduce it, and what I'm going to do is, of course, compute our norms. Norm of V1 squared is really big. Of course, something like 8.71 times 10 to the 15. Norm of V2 squared is something like 8.33 times 10 to the 13. So a little bit shorter. This is shorter than that, so we swap them. Right? And then we subtract a multiple of V1 from V2. We compute M, and this gets us 10. Right? We do M as the dot product of these two divided by the norm of V1 squared, so divided by that, and we got like 10.2 or something like this. We round it up to, so it's like 10.22, something like this, and then we just round it up to 10. Okay, so then we can replace V2 with V2 minus MV1. We got a new V2. And the new vector as norm equal to 4.11 times 10 to the 12. So we reduced by an order of magnitude here, right? This is again smaller than V1 squared, which, sorry, what we did is we swapped. So we replaced this one with this one. and then now this is smaller than the new, this had become V1, right? So we always reduce the biggest of the two. Okay. So then we swap again. This becomes V2 again. This becomes V1. We subtract it again. We compute the new M, and we get 4.502. We round it up to 5. We replace. We get a new norm. It's going to be 1.01 times 10 to the 12. So now these are our two vectors. Right? And we keep iterating this, and we do it over and over again. And I'm not going to do it over and over again, but you see it in the table here. That at the end of the day, the first few vectors are big, and then you keep going down. At the end, you stop. But look at these vectors now; they're very small. Okay, this is the final basis. In this particular case, this is also a solution to SVP because you find the shortest vector as well. Okay, but otherwise we can use this as a good basis, for example, to apply our decoding algorithm stuff. And of course, yes. So the LLL algorithm kind of works along these lines, right? And it's a little bit more complicated, but the idea is similar. It uses the idea of the Gram-Schmidt reduction of a basis, and then it does kind of the similar process. It basically projects vector onto the span of the other ones, because now we're not in just one two-dimensional, but like we're in multiple dimension. So you essentially start from a basis and then start reducing by subtracting multiples, and you have loops with some size control. In the previous one was easy because like we just have two vectors. If the thing does work is shorter than the previous one, then I swap and continue. Otherwise, it doesn't. Here I have a little bit more complicated stopping condition. So I think the best thing I can do here, because we also don't have a lot of time, is just show you what the algorithm looks like. You see, so you start from a basis, and then you start setting up the first vector, you loop one of the other ones, right? And this size reduction recalls the one that we had before with the M. Does the same thing. We're subtracting multiples, like projections essentially, right? And the condition that you see here, which is the lowest condition, is kind of like, okay, you want that to be smaller in a sense than the previous one, right? When you want to do things with criteria. And then otherwise you just swap them and finish there. Okay? And in the end, after you do this, you have a new reduced basis. And it says here at each step, the new V1 star VK star, this is like the previous, is the orthogonal projection of like not just one vector, but like the span of the previous vectors. Okay? And so yeah, in the end, you end up with a much reduced basis. Okay? And the hope is that the new basis has a much better orthogonality ratio. And you can prove, in fact, that the algorithm always terminates. And if we set B to be the maximum of the norm of the VI that we started with, then the algorithm executes no more than O n squared log n plus n squared log B steps of the loop. Okay, and so this is actually polynomial time algorithm. Okay. Of course, the problem is that this has to be efficiently implemented, right? And you have several challenges there. The book has several pages describing this in detail. But essentially, like this is the main threat for lattice crypto systems. Okay, and there are obviously like several improvements and generalizations. One of them is called BKZ, again from the authors, which are Korkin and Zolotarev. and the B stands for block, so it works block by block. So yeah, instead of like swapping, you just kind of like replace an entire block with another block. It's kind of like one of the optimizations that you can imagine that you can do in these situations. And so essentially, the algorithm is kind of polynomial time, but then the n is really big. And because it's like n squared log n, essentially, then you get like a really big complexity there. Okay.
So polynomial time algorithm, but with a high constant term.
Yes. So essentially, standard LLL and then the improved LLL basically require a block size that kind of like grows linearly with n, and then so I mean, to be more precise, I mean, yeah, so you can take this to be like big enough. I mean, it's a little bit hard to oversimplify, but essentially, like you can make this big enough so that it's not a threat. But that's kind of like the idea of the algorithm. Okay. You reduce the basis. If you can do this efficiently, then you can just apply the normal decoding algorithm, and it's likely to succeed. And this was just a panoramic. So at this point, we're not going to say much more about. I mean, there's a lot of literature, of course, on lattice cryptosystems, and it quickly becomes hard with the notation and the mathematical notions, harder than the coding theory ones. From our point of view, there's like a lot more in terms of also like how these things are distributed, and so feel free to have a look at the rest of chapter 6. That has like a lot more details, and also other crypto systems. For example, a very important one, which is called ntrue, is also lattice based, but the lattice is formed in a different way, like less obvious way than GGH. It's like a polynomial ring. So, and then like we will see in the next couple of lectures, which are the last ones, a few more things, and we'll see the lattices are an important player in the scenario. Okay, so I think this concludes the lecture for today.